Hello, today we're going to talk about strong and weak acids and bases. When we use the word strong means that it completely breaks down into ions, completely dissociates. Weak acids and bases only partially dissociate into ions. And so therefore you have very different properties of strong and weak acids and bases. So there are 7 strong acids that you should know. And some people include different ones on this list, but these are the 7 that I was taught. So HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. So hydrochloric, hydrobromic, hydroiodic, nitric acid, sulfuric acid, chloric acid, and perchloric acid. Those ones are strong. These ones completely dissociate. And if it's not on this list of strong acids, then it must be a weak acid. And then there are 8 strong bases. Again, different people include different things on this list, but this is what I was taught. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. And then calcium hydroxide, strontium hydroxide, and barium hydroxide. And I draw it like this because this is how they're located on the periodic table. So those are the 8 strong bases. And if it's not on this list of strong bases, it must be weak. And so when you have examples of these, if you have like, let's do a really common weak acid, which is acetic acid. So HC2H3O2. This one can dissociate into hydrogen ions and acetate ions. Like this. But because it's weak, only some of these break down into ions. And once they are in ions, they can form back together again. So it forms an equilibrium system where you get like this kind of back and forth, where some of them are breaking down into ions and some of them are combining back to the original acid. And this is still your acid, and this is still your conjugate base, but you wind up with this equilibrium system. And if I were to write an equilibrium expression for this, I would have the products over the reactants like this. And we would call this a Ka because that's an acid dissociation. Now you're not going to see that for these 7 strong acids because they 100% dissociate. Even if they do form a very temporary interaction again, they just immediately break apart, and it's not forming that equilibrium system. Let's look at a base example. Now it's easier with weak bases to show them reacting in water. So let's do like ammonia as a weak base because it's not on this list of strong bases. So in water, what happens is the ammonia is going to steal a hydrogen from water to form ammonium and leave behind a hydroxide ion. So in this case, this is our base, this is our conjugate acid. The water is acting as an acid, and the OH is its conjugate base. But in this case, I'm going to just focus on the ammonia. And because it's weak, the hydroxide and the ammonium can form back together to, or can basically give off its hydrogen and recreate water and ammonia. And so it creates this equilibrium system where it can go back and forth between the 2 sides. And so you can write a K expression for this. But we don't include water because it's a liquid. So I have my ammonium times my hydroxide all over my NH3. I don't include the water, and this is called a Kb expression because it's a weak base dissociation. We can use a few methods to distinguish between strong and weak acids and bases. A really important one is conductivity because it's just like a strong electrolyte and a weak electrolyte. Strong acids and strong bases, because they completely break down into ions, are going to be much more electrically conductive than weak acids and bases will. You can also use rate of reaction. because the strong acids and bases can dissociate completely, they're going to react at a faster rate because more ions are available right at the start, versus weak acids and bases, like you'll eventually be able to react them all, but it will take more time as they have to dissociate as you're using them up. And then the last one is pH, and I really want to focus on this pH. So this is really dependent on concentration. So I'm going to use like HCl and HC2H3O2, my acetic acid, as an example. So this is a strong acid versus a weak acid. Now, if I have a equal concentration solution, let's say I have 0.01 moles per cubic decimeter, 0.01 moles per cubic decimeter. So same concentration of both. That means that the pH of the HCl will be less than the pH of the acetic acid, because all of this will break down into hydrogen ions, but only some of the 0.01 moles per cubic decimeter for the acetic acid. That's if they have the same concentration to begin with. Now, if I have like a, let's say I have like 1 × 10⁻⁸ moles per cubic decimeter, compared with the same 0.01 moles per cubic decimeter of the weak acid, then you might see the pH of the weak acid being greater. I'm sorry, of the strong acid being greater. It's very much concentration dependent. So don't just automatically assume that the strong acid definitely has a lower pH. However, if you do have the same concentration, you know that the strong one is going to dissociate more and will have a greater impact on the pH than the weaker one. So be careful there. Just make sure you're comparing apples to apples in that situation. But yeah, those are different ways that you can actually experimentally distinguish between the two. Okay, so this one says, write an equation to show how ammonia can act as a weak acid when dissolved in water. Now we did an equation a couple slides back of ammonia acting as a weak base when dissolved in water. But ammonia is kind of cool, and it can do some interesting things because it has some hydrogens there in water. Okay, it could steal a hydrogen from the water and act as a base, but it could also give up a hydrogen, an H2 negative, and give its hydrogen to the water to form hydronium. So in this case, it's acting as an acid, and because it's weak, it's not on my list of strong acids, it would form an equilibrium system like this, where this then would be your conjugate base. And then you'd have hydronium ions, which are lowering the pH. Now, this doesn't happen as much as ammonia acting as a weak base, but it is interesting. And so you need to pay attention to terminology because they might throw weird situations like this one at you. Okay, so here's an interesting question. Which one has the stronger conjugate base, H2CO3 or H2SO4? I'm going to write this out really quick. H2CO3. When it dissociates in water, because this is a weak acid, you're going to have an equilibrium system, and you'll be left with the HCO3 minus. And so this is our acid, and this is our conjugate base. The sulfuric acid, H2SO4, is a strong acid, so a single arrow, that will also lead by an HSO4 minus. This is our acid, and this is our conjugate base. So it's saying which one has the stronger base? Well, that means we want to know which one is more likely to go in the reverse direction and attract a hydrogen to it. So you see stronger conjugate base, which one's more likely to attract the hydrogen to it? That's this thing, because you actually have a decent possibility of it reforming into H2CO3. Whereas with the sulfuric acid's a strong acid, you don't really see that happening at all, where the HSO4 minus is going back to the hydrogen and reforming the original acid. So in this case, the H2CO3 has the stronger conjugate base. And so a good rule of thumb is that the weaker the acid, the stronger its conjugate base. The weaker the base, the stronger its conjugate acid. Okay, so this one says, well, how would you expect the equilibrium constants of strong and weak acids to compare? So again, we're taking our acid. I'm just going to use HA as a generic acid. And so my Ka value is going to be my H plus times my A minus all over HA. And so if I have a strong acid, that means you basically have none of this left over. Maybe a few molecules in the whole thing. But effectively your Ka is going to be huge because effectively it's all on the top. So all of them are ions. Much, much larger value for Ka. Compared to weak acids only partially dissociate. Really. So you're going to see a decent amount of the HA left over. The original acid is left over. So the value of Ka is going to be much smaller. You're going to have a lot more of the HA present, which is going to bring down the overall value for the Ka. Now this also links to periodic trends. And so you've got our H, like halides, right? So let's say HF, HCl, HBr, and HI. As you go down, it gets more acidic. That's because iodine has the largest radius. Because iodine has a bigger radius, it's much easier for the hydrogen to leave because it has weaker Coulombic attractions to the hydrogen. They're further apart. Fluorine, on the other hand, has the smallest radius, and it can get much closer to the hydrogen ion, form very strong Coulombic attractions with the hydrogen, so the hydrogen doesn't leave very easily. So like that trend as you go down, it makes the hydrogens more and more easy to leave, which makes it act more and more acidic. So make sure that you are paying attention to any kind of trend. You want to think about Coulomb's law. Now it says, what physical and chemical properties can be observed to distinguish between weak and strong acids and bases of the same concentration? Notice that, same concentration. So you could use pH to distinguish. So strong acids are going to have a lower pH than weak acids at the same concentration. Strong bases are going to have a higher pH than weak bases of the same concentration. And then you can use rate of reaction. Strong ones are going to react faster. You could also use conductivity. Strong acids and bases are more conductive than weak acids and bases.